Today we're going to talk about socket data structures. We're going to talk about how to get interface information on Windows, how to get interface information on Unix, how to decode that information, and then we're going to go into our lab listing network adapters from C, which is in Chapter 1 of our book. The Berkeley Socket API is from 1983. IP version 4 went live on January 1st, 1983. The APIs and the data structures associated with the Berkeley Socket API are complex. They use pointers, structs, type defs, and even unions, which is a C feature that most programmers tend to avoid using. Dealing with these complex data structures, it's easy to be intimidated and to feel imposter syndrome, where you feel like you should be able to understand it, but you're having trouble with it. But I want you all to not panic. People do not program these APIs from memory. They're usually looking at documentation while they're using these APIs and data structures. In addition, we have not yet completed our review of TCP UDP theory, so not all of these APIs, you don't have all the background yet. So don't be afraid and don't panic. Let's just get into it. And it is helpful to keep a list of useful network library functions. So it is useful to take notes of all the different library functions that you learn. For Windows, docs.microsoft.com is your friend. It includes syntax and code samples for Windows functions. Here's an example of the WSA startup function, which we use and our book has us use, but does not explain really what it's for. So whenever you find a Windows function that you're not familiar with, I encourage you to look it up in docs.microsoft.com. Please make sure to check that out. It's also helpful to find header files on your operating system. So, for example, there's the winsock2.h, iphlpapi.h, and ws2tcpip.h header files that are included with some of your programs. You can use File Explorer to find those header files, and then you can browse through them, and that's useful. But when you're using the File Explorer, by default, it just does a quick search of your home directories. Make sure to set it to search the entire PC, and then you can easily find the header files in the installation directories of your compiler. I have good news and I have bad news. The good news is all we're going to do with our first lab is to traverse a linked list and print out some data. The bad news is the linked list is big and intimidating. Don't be intimidated. It's just a linked list with a bunch of data. The GetAdaptersAddresses function returns information about addresses associated with the adapters on the local computer. You can pass in the family to identify whether you want to return IPv4 or IPv6 or both. You can pass in flags so that to minimize the amount of information that is returned, so that we don't have to sort through a bunch of data that you don't want. For example, if you don't want multicast addresses, you can pass in a flag so that it does not give you any multicast addresses. You pass in a pointer to a pointer to memory that can be used for adapter addresses, and then the function will fill up that location. And you also pass in a pointer indicating the size of your memory location. That has two benefits. One is that it tells the function how much space they have to fill up adapter addresses so they don't overflow. And then the second advantage is if your adapter addresses data structure does not have enough space for the amount of data of address information, then it will return, it will modify the integer that the pointer is pointing to indicate the required size. Here is the data structure returned by the GetAdapterAddresses function. You can see we have a struct, and it has its struct tag is ifaddrs LH with an underscore at the front, and then it's immediately type deft so that it has a type name ifaddrs LH without the underscore in the front. In addition, the type def also specifies a pointer to ifaddrs LH, and there is also a type def pointer ifaddrs without the LH. This is a standard setup for many of the Windows data structures. They always have a struct tag with an underscore, and then they immediately type def it without the underscore, and then they also type def it with a pointer, which by prepending the letter P to the type name. Looking at the data structure itself, it's big and long and intimidating, but all it is a linked list. We have a next, which points to the next adapter addresses. So this is a linked list, and we'll just traverse the linked list until the next is null, and then we're done. Included in here, we have the first Unicast address, which is a pip adapter Unicast address LH, and we'll see that data structure in a minute. That is also a linked list. So in fact, this linked list is a linked list of adapters, and then each adapter has multiple Unicast addresses, and the first Unicast address is included. We have appointed the first Unicast address, but that will just be itself a linked list. And then there's other information about the adapter. For example, here's the transmit link speed, the receive link speed. That's useful information to have. Here's a simple example of using the GetAdapterAddresses function. I've created a variable addresses, which is a type pointer to IP adapter addresses, and I dynamically allocate it 15,000 bytes of memory, and then I run the GetAdapterAddresses function. My family and flags are set to 0, so I'm getting all information about all interfaces, and then I pass in my 15,000 byte sized space for the pip adapter addresses data structure, and I pass in the address of the size 15,000 bytes that is available, and I get, and I don't test for any errors in this simple example, and then I get the result, and then I traverse. While I traverse through the addresses linked list, I print out the interface name, and I print out the friendly name, and then I go to the next address. And so then here you can see I have the interface name and I have the friendly name for each adapter, and I go through that for each adapter until I'm done. So just printing out some of the information. I didn't print out the addresses in this example. You'll do that in the lab. Here's the IP adapter Unicast address LH structure that we saw. We had a first Unicast address in our adapter linked list data structure, and that points to this linked list. So this again uses the standard Windows naming convention where we have a struct tag with a underscore, and then we have a type def for the struct so that we have the same name, IP adapter Unicast address LH without the underscore, and then we have a pointer to the IP adapter Unicast address LH where we've prepended the P onto the name. So if you see the P at the start again, that's usually a pointer in the Windows realm. And then inside the structure itself, it has some information about the address. It has the socket address. All of this data structure is complex. We'll get to that in a minute. But it has the address, it has some lifetime information, and then it has the next Unicast address on the same adapter, because again, this is a linked list. So if we want to print out all the Unicast addresses on a particular adapter, we need to traverse this linked list and print out the socket address for each one. Here's that LP socket address we saw before, or socket address here. So socket address struct tag with the underscore, type def to socket address without the underscore, and we have p socket address, which is a pointer to the socket address, and we also have lp socket address, which is also a pointer to the socket address. And then we have inside it, we have an LP sockaddr, which is also a pointer to a socket address represented as a sockaddr data structure, which we'll see in a second. And then we have an integer indicating the sockaddr length, because the sockaddr data structure might be of different lengths. Finally, we're getting to an address. We have LP sockaddr, which is a pointer to the sockaddr data structure. The sockaddr data structure, it starts with the family, and then it has 14 bytes for data. And the reason for that is there are multiple types of sockets with different types of addresses. And so they wanted to make the sockaddr structure generic. So here we have a 16-byte data structure, and because it would be a short, which would be 2 bytes in this case, and then we've got 14 bytes here. So it's a 16-byte sockaddr data structure, which you can cast it to different types of sockets. One of the types of sockaddrs you can cast it to is the sockaddr_in. This is also a 16-byte data structure, which starts with the family, and then it has the port number, which that's referring to the TCP or UDP port, which is 16 bits or a short. And then it has the IP version 4 address, which is 4 bytes, 32 bits. And then it has 8 bytes of zeros to use up the rest of the space. So this is a sockaddr IN for an IPv4 data structure. The problem is that when IPv6 came out, the IPv6 sockaddr would not fit inside this data structure. So they have a new data structure called a sockaddr storage, which is a total of 128 bytes in size. So if you need to create a sockaddr, what you do is you allocate 128 bytes for your sockaddr storage, and then you cast it to a sockaddr_in or a sockaddr_in6. So in the prior data structure, when it was pointing at a sockaddr, it's probably not pointing at a 16-byte data structure. It's probably pointing at a 128-byte data structure. And that's why some of those prior data structures had the length and everything. The first thing in each of the data structures is the family. So you can look at the family and see if your family is IPv4 or IPv6. If your family is IPv4, then you cast your sockaddr to a sockaddr_in, and then you can read the address. Or if the family is IPv6, then you cast it to a sockaddr_in6, and then you can read you still have the family, you still have the 16-bit port information, you have the flow info, which you might remember from the IPv6 header, and then you have the IPv6 address associated with it, and it actually also includes an IPv6 scope, which might indicate whether the IPv6 address for the socket is link local or site local or global. So here's the sockaddr IN6, and then we have some type defs. So this sockaddr thing, where we have multiple different structures, it is non-intuitive. Just remember, you check the family, you get your sockaddr, you don't believe that it's just a sockaddr. Instead, you check the family, and based on the family, you cast it to a sockaddr_in or sockaddr_in6, and then you can read your data. Here's the inaddr data structure on Windows, which was included in the sockaddr_in in the prior slide. The inaddr, it's a union, and we can access the data in multiple ways. We could access it with each of the 4 octets as an unsigned car, which is a an unsigned car, of course, is an 8-bit unsigned. You can think of it as an 8-bit unsigned integer, or we can access it as a 32-bit unsigned integer. So just one unsigned integer for the whole address. It also has the option to access it in groups of 16-bit, the IPv4 address in groups of 16 bits, but I don't think that's very useful. So you usually want to access it either with the 4 octets individually or one at a time. And these 4 octets, you can bet it's in big Indian order. For the IN6 adder, over here we have the IN6 adder. IN6 adder has 16, an IPv6 address has 16 bytes, 128 bits. We can access it by the 16 bytes. Or another way of looking at an IPv6 address is by, there are 8 hextets. Each hextet has 16 bits, so 8 words, each is a short, so there's our 8 hextets, and there we go. One of the inconvenient things about dealing with IPv6 addresses is most programming languages do not have an unsigned 128-bit integer. It would be nice to just be able to access the IPv6 address as a unsigned 128-bit integer, but not available in C by default. Here's a quick program to traverse the addresses linked list for each adapter. So we have our main, and we get our PIP adapter addresses data structure, and then we traverse the addresses. So for each adapter, we are printing out the interface name and the friendly name like we did before, and then I call the function print adapter addresses where I pass in the first Unicast address. Up here we have the print adapter addresses where I passed in the first Unicast address, and I traverse the linked list. So while the addresses is not null, then I print the socket address and then go on to the next address. Here's the print socket address function, which was called by the prior slide. We passed in our socket address, we deal with our indirection and get a sockaddr, and then we check the family. And if the family is AFINET, then that means that it is a sockaddr_IN, and we're dealing with an IPv4 address. And so in that case, I pull out the IPv4 address here. The data structure for the IN adder is a bit painful. We have an S_UN, and then inside it we can access our union via the SUNB, and then we have to access each byte. So I think this SUN, the W refers to the word, and the B, accessing it by word, and then the B refers to accessing it by byte. You can see that we have we get our SYN adder out of the sockaddr_IN data structure, and then we have our address, and then here I'm accessing each of the octets, so it's adder, so the IN adder, and then I have to do a S_UN, and then an S_UNB, and then a .S_B1 to get the first byte, and that's our most significant bit and or byte, and so we put it there. And then I do it 3 more times. It scrolls off the screen here, so you don't actually see the B2, B3, B4. But that way I can get the 4 octets if it's an IPv4 address. If the family is AFINET6, then it's IPv6, and so then I cast my sockaddr to sockaddr IN6, and then I can access the elements, and in that case I just do a loop accessing each of the hextets and printing it in hexadecimal with the colon. And here is the output. You can see for each adapter I have the interface name and the friendly name, and then I print out the addresses. In some cases it's an IPv6 address, in some cases it's an IPv4 address, and then I'm just traversing my linked list here. So I have my linked list of adapters, and then for each adapter I have my linked list of addresses, and then for each address it might be a sockaddr_IN or a sockaddr_IN6 that I am accessing. You might be thinking that there has got to be a library to get the information out of the sockaddr because that's just painful. And the answer is there is. There's the get name in Windows. There's the get name info function where we pass in our pointer to the sockaddr and we pass in our sockaddr length. If you remember, we got those from one of our earlier functions, and we pass it in some flags to tell whether we want the host name or IP address. And by default, the service is generally TCP, but we could pass in a flag to say we want the name of the service for the UDP, and then as the output, we'll get a buffer for the host name or address name, and then we'll get a service buffer, which is the buffer for the service name. Now remember, in this example, we're getting only IP addresses out of our sockaddrs, but socket addresses, the data structure includes both the IP address and a port number. And when we say port number, that also can refer to a service. So for example, port 443, the service would be HTTPS. So with the get name info function, we can get the data out of our sockaddrs without the extreme pain of traversing that data structure. Let's move over to Unix, which includes macOS and Linux, starting with documentation. And one part of documentation on Unix are the man pages. So here we're using the man command to look up the man page for the GetIfAddrs function, and it gives us information about the function, the header files that are required, the functions itself, and it even gives me documentation on the data structure where you can see that it's actually returning linked lists again about interfaces. It's also helpful to be able to find where your header files are, and sometimes it's surprisingly difficult to actually find the header files. Here's a find command. I changed to the root directory, and then I changed to the /library developer directory, which is, at least on macOS, is underneath that is where all the development header files are included. And then I started a find from the current directory for the file ifaddrs.h and to print them out, and it gave me 3 different versions with 3 different macOS SDKs. And then I went to the one I wanted, which was macOS 11.3, the most recent, and found the ifaddrs.h header file, and I just viewed the file, and there I can see my ifaddrs data structure. So sometimes when you're looking up data structures, you want to find them via the header files, and sometimes it's just easier to use the man pages. When you get to the header files directory, sometimes you're looking for a particular data structure. In this case, I'm looking for the struct sockaddr data structure. And so I go to the directory, and then I use grep to search for all files, in this case ending with the .h in the current directory or one subdirectory, where the lines start with struct sockaddr, and I found too many hits. So I narrowed it down by searching for lines that started with struct sockaddr and then a curly brace, and I found my one hit. So the syssocket.h file is where the struct sockaddr was actually defined, and that helped me find the sockaddr and then the related sockaddr underscore. That was my pursuit of all of the different variants of the sockaddr data structure. Here we are with the macOS version of the sockaddr family. You'll also probably find similar sockaddrs on all variants of Unix. The generic sockaddr data structure, again, is 16 bytes in total size, and it starts with the length of the address. So for an IPv4 address, this would be a 4, and for IPv6, this would be 16. And then the next byte is the family, whether it is IPv4 or IPv6, and then based on that, you cast it. The sockaddr, if it's an IPv4, then you'd cast your sockaddr to a sockaddr IN, which is also 16 bytes in size. If you find it's a sockaddr, if the family is IPv6, then you would cast it as a sockaddr underscore IN6, because you can bet that even though it looks like it's a sockaddr, it was actually a sockaddr storage, which has 128 bytes of storage. So similar deal as Windows. Here is the GetIfAddrs function. We pass in a pointer to a pointer of ifaddrs, and then we execute the call. The function allocates memory for us and gives us our data structure. Our data structure is a linked list. So we have our ifaddrs, and then each ifaddr has a next in there until the last one is null. We get one of these for each interface. Each interface has an interface name. It has flags. It has the address, which is given to us as a sockaddr. As you know, a sockaddr, it could be an IPv4 sockaddr, it could be an IPv6 sockaddr. We have to look at the first part of the sockaddr to figure out what type it is, and then cast it to either a sockaddr IN or a sockaddr IN6. It gives us a net mask. It gives us a destination address if it's a point-to-point interface, which we haven't talked about yet. That'd be like for a VPN, for example. And then we get some interface address-specific data. Here's a simple example of using GetIfAddrs. So I've created my ifaddr. I've created an addresses, which is a pointer to a struct ifaddrs, and then I pass its address so the address of the pointer. So it's a pointer to a pointer to the GetIfAddrs function, and ideally I should check the return value for errors, and then I traverse the linked list, printing out the interface name, and then going on to the next one. And then I use the free interface addrs function to free up the memory, since it was dynamically allocated within the GetIfAddrs. So this frees up the entire data structure, after which I should not access the data structure, obviously. And here's my sample output. Note that I'm getting, for example, 4 ifaddrs output for my loopback 0, and that's presumably because there are 4 different types of addresses on my loopback. And then I get, for EN0, which is my main wireless interface, I've got 1, 2, 3, 4, 5, 6 ifaddrs, and so that way I get my 6 addresses from it. Here is a more complex ifaddrs example. Again, I create addresses, which is a pointer to a struct ifaddrs, and then I pass the address of my pointer into the GetIfAddrs function and get my data structure. Then I traverse the linked list. I get my sockaddr. For each traversal, I get my sockaddr, and I test the family. And if the family is AF underscore INET, which means it's IPv4, then and only then I will try to print out the IPv4 address. So in that case, I print out the name just so I can see the name of the interface for my reference, LO0. And then since it's an AF INET, I take my sockaddr part of the I take the sockaddr and I cast it as a sockaddr underscore IN, which is the IPv4 version of the sockaddr. And then I access it and I get out of it an unsigned 32-bit integer, which represents the IPv4 address. And then I attempted to print out the 4 octets using math. And so, for example, for octet 1, I was attempting to get the 4th octet, so I was doing an integer division by 2 to the 24th power, and then octet 2, doing integer division by 2 to the 16th power modulo 256, and then and so on. So for the 4th octet, it was just a straight up modulo 256 to get the last octet, and then I printed it out. But I have a problem, and my problem is instead of printing 127.0.0.1, I printed 1.0.0.127. And the reason for that is my computer is Little Indian. However, data in the sockaddr is in Big Indian format. So this was not the direction that I expected. So 2 ways to solve this. One is to do octet 4 first and and reverse them, or of course I could use the network to host long function to convert my 32-bit unsigned integer from network byte order to host byte order. And then I continue traversing my linked list to the next address until addresses are done, and then of course I free up my data structure. inet NTOA is an older function which converts an IPv4 network address to an address. So down here you can see the ITNTOA. We pass in an INAddr, which is an IPv4 structure, and it gives us a pointer to a string. Here's an example using it. It's the same as the prior example, except once we get our 32-bit unsigned, or once we get our INAddr structure, we pass it into inet_NTOA and just print that out, and you can see it prints out the IPv4 addresses in the correct byte order. For IPv6, we use the inet NTOP function, which is newer and can work with IPv4 or IPv6. In this case, we use it with IPv6. We create a buffer for our string. We set the buffer to 0. We pass in, we call our function inet NTOP. We identify the address family as IPv6. We pass in our IN6 adder, which is the address of our IPv6 socket. We pass in our destination buffer and the size of our destination buffer. We want our destination buffer to be large enough to handle any IPv6 address here. I just used 100 bytes, which is a bit wasteful, but definitely going to succeed. And then we get our address, and we as long as the return value is not null, we print out our destination. And so here you can see this is an else if with the rest of our IPv4 code above, and there's our friend inet NTOA for the IPv4 version there, and then you can see for each interface we're printing out its IPv6 address or its IPv4 address. Unix also has a getNameInfo function, which is also worth looking up and considering. Let's review what we learned. Socket-related data structures are old and crusty. In order to deal with them, you have to know your documentation sources. docs.microsoft.com is excellent. Man pages are helpful. Internet searches and Google are your friends. Know where to find the include files on your system. On Windows, we can get information about adapters and interfaces on adapters with the GetAdapterAddresses function. On Unix, it's the GetIfAddrs function. We reviewed our data structures, particularly our Windows data structures and our Unix data structures. We reviewed the different types of sockaddr and how you allocate a sockaddr storage, which is a large 128 bytes, and then you can cast it to whether you need an IPv4 or an IPv6 sockaddr. These APIs and structures are difficult, but with examples, you can get through it. So don't feel imposter syndrome. In Beej's guide, he refers to some of these sockaddr unions, data structures, as the scariest union in the history of the internet. So we have a lab, Network Programming with C, Chapter 1, listing network adapters from C. There's a Windows version and a Unix version. For the homework, you need to do one of them based on which operating system you have. You're not required to do both of them. So if you're on a Windows system, don't start typing in the Unix version. It's not going to work that well. Type in the code yourself. Do not download it. Feel free to play. Adding functionality, printing out the link speed, for example, would be a great thing. Add comments. That's how you prove to me that you understand what you're programming. So that's a significant part of the grade. and turn it in via Canvas, see the canvas for the due date. And if it's one file, you can just include the file. If it's a whole project, you can zip up the project and give me the zipped project.